In this video, we're going to look at the testing procedure for the analysis of variance hypothesis. Remember, the analysis of variance hypothesis is that you have a set of groups or set of populations, and the null hypothesis is that all the means are exactly the same. So suppose if you have C groups, then mu sub 1 all the way through mu sub C, they are all the same. All population means are equal. I suppose the alternative hypothesis is that not all the population means are equal. Okay, so there is only one form of the hypothesis, unlike in the previous cases where there are three different forms of the hypothesis that we looked at: two-tailed, the left side one tail and right side one tail. In ANOVA, there is only one form. All means are same, as opposed to not all means are equal. So that's the only form. If all means are same, then the factor is not significant. That is, the difference in the case of GPA, if all the means are same, then as far as GPA is concerned, the major, the College of Business major is not a significant factor. So that's what your conclusion will be. Or if you reject the null hypothesis, then your conclusion will be the average GPA, or I should say this way, the major selected by the student is a significant factor in predicting what the GPA, average GPA will be. Okay. So how do you test this hypothesis? Now if the null hypothesis is true, then all the means are same and you have to assume normal distribution for each population, and we make a further assumption for testing this hypothesis, and that is all the population variances are the same. Okay. Now we will look at a hypothesis test whether that assumption is a reasonable one or not. But for the moment, okay, that assumption is made. If all the variances are the same and if null hypothesis is true, then there is only one population. All the means are same, all the variances are same, all the variances are the same. So which means there is only one population. Okay. As opposed to if the null hypothesis is not true, then you can have any one of these situations where all the means are different or just one is different from the other two. Okay. But the variance of the different populations are still the same because we are assuming that the variances are equal. Okay. So this is the situation. So what we're going to do is we look at the variance in the sample and we're going to split it into two parts. So SST here is total sum of squares, which is a measure of the variance in the sample. Okay, SST, so total variation in the samples. Okay, you have a bunch of samples, all the samples taken together, the total variation, and we divide it into two parts. The sum of squares, the variance attributable to the differences in the groups. That's your sum of squares among the groups. And then sum of squares within the group. So within each group, how much variability is there? So variance attributable to the differences in the groups and the variance attributable to the difference within the group. Now if there is no significant difference between the factors, then you would expect the among the groups portion of the variability to be small. If the groups are all the same, then you don't see any variability among the groups. So SSA will be small as opposed to SSW. On the other hand, if the groups are all different, then the variance attributable to the differences in the groups will be large. SSA will be large. So that is the principle based on which we will make the test. So first thing to do is to compute these sums of squares, and there are formulas for that. Okay, so this is the formula for SST. Okay, and here X double bar is the overall average of all the samples. Okay. And then SSA is you take individual sample means, okay, subtract from the overall sample mean, square it and multiply by the sample size. So this is the formula for the among the group variability portion. And then we have, okay, when you take that SSA and divide by C minus 1, number of groups minus 1, and that is the degrees of freedom for among the groups, then what we get is a mean square among the groups. So SSA is sum of squares, divide by the degrees of freedom, we get mean square. Okay. Now remember, if the different factors, if the different groups are significantly different, SSA will be large and MSA would correspondingly be large as well. Otherwise, it will be small. Okay. Now, the SSW within groups is within each group, you look at the difference between the individual observation and the mean within that group. Square it, okay, and that's your SSW. And the degrees of freedom for this is n minus c, with n being the total sample size of all the samples put together, minus c. Okay. Now that's your mean square within groups. Okay, so here is a summary of what we have so far. MSA between groups, within group, and here once again I repeat myself, if the different groups are significantly different, MSA will be large. Otherwise it will be small compared to MSW. So now if you take all of this information and present it as a table, that is called a one-way ANOVA table. So we have among groups, within groups, total. The degrees of freedom, C minus 1, N minus C and N minus 1. SSA, SSW and SST, we looked at the formulas for these. And you divide the sum of squares by the degrees of freedom, you get the mean squares. And now if you take a ratio of these two are different forms of variance. So this will be like a ratio of variance that we saw in a previous case, previous video testing for the equality of variances. Now if the means are different, if the different groups are different, then MSA will be large, F stat will be really large. On the other hand, if the groups are all the same, then MSA will be small and F stat will be small. So we have to have a critical value for the F stat value, and once F stat is greater than the critical value, then we'll reject the null hypothesis. So the table value is F sub alpha with these two degrees of freedoms. We will get the F critical, and then if F stat is greater than or equal to that critical value, we reject the null hypothesis, otherwise not. Okay, so here is the F sub alpha or F table value. And we can also develop a p-value using the F dot dist function. Based on p-value also we can arrive at a conclusion for the hypothesis. So here is a worked out numerical example in your PowerPoint where we have 3 different clubs and we want distances, whether there is any difference between the clubs. So here the factor is golf club, and there are 3 different treatment levels: golf club 1, 2 and 3, and the response variable is the driving distance, and we want to see whether the average driving distance is same for the 3 different golf club makes. Okay. We compute the X bar value for each sample and X double bar, and then we plug in the values into the different formulas. Okay. And we compute MSA and MSW, compute F stat, F table value, and arrive at a conclusion. And we can present this as a ANOVA table, where here is the ANOVA table, where between groups, within groups, sum of squares, degrees of freedom, mean square, and F, and so on. So what we're going to do is we're going to look at an Excel example of this ANOVA computations next.